Chapter 1 Single Area OSPFv2 Concepts. In this chapter, we are going to cover 3 sessions. 1.1, that's the OSPF features and the characteristics. 1.2, OSPF packets. And 1.3, OSPF operation. Without further ado, let's start. 1.1.1 Introduction to OSPF. This topic is a brief overview of the Open Shortest Path first. The OSPF protocol, which includes single area and multi-area. OSPFv2 is used for IPv4 networks. OSPFv3 is used for the IPv6 networks. The primary focus for this entire module is the single area OSPFv2. OSPF is a link state routing protocol that was developed as an alternative for the Distant Vector Routing Information Protocol, the RIP. RIP was an acceptable routing protocol in the early days of networking and the Internet. However, the RIP resilience on hop counts, as the only metric for determining the best route quickly, become problematic. Using hop count does not scale well in larger networks with multiple paths of varying speeds. OSPF has significant advantages over RIP in that it offers faster convergence and scales to much larger network implementations. OSPF is a link state routing protocol that uses the concept of area. A network administrator can divide a routing domain into distinct areas that help control routing of the traffic. A link is an interface on a router. A link is also a network segment that connects two routers, or a stop network such as an Ethernet LAN that is connected to a single router. Information about state of a link is known as the link state. All link state information includes the network prefix, prefix length, and cost. 1.1.2 Components of OSPF. All routing protocols work in a similar way. They use routing protocol messages to exchange routing information with other routers. As routers receive this information, they build data structures such as routing database or topology tables. These data structures are then processed by a routing algorithm, which calculates the best paths to different destinations and determines which routes should be added to the routing table. Now let's talk about how OSPF routers communicate with each other. OSPF routers exchange routing information using 5 different packet types. Each packet has a specific job. Together, they help routers discover neighbors, exchange network information, and keep their routing database synchronized. Let's go through them one by one. The first packet is the hello packet. As the name suggests, it is used to introduce one router to another. Routers send hello packets to discover neighboring OSPF routers and remain those neighbor relationships. Think of it as saying, "Hello, I'm here. Are you an OSPF router too?" The second packet is the database description, or the OBD packet. After two routers become neighbors, they don't immediately exchange their entire database. Instead, they first exchange a summary of what they know. This allows each router to quickly determine whether an information is missing. If a router discovers that's missing some information, it sends the third packet called a link state request, or LSR packet. This packet simply asks its neighbor, "Can you send me details for the specific information?" The neighbor responds with the fourth packet, the link state update, or LSU packet. This packet contains the requested link state information. It's also the packet used whether there is a change in the network, such as a link failure or the addition of a new network. Finally, after receiving the update, the router sends the fifth packet, the link state acknowledgement, or LSACK packet. This confirms that the update was received successfully, making the exchange reliable. So remember, these 5 packets work together throughout the OSPF process. Hello, discover and maintain neighbors. DBD exchange the information of the database. LSR requests missing information. LSU sends the requested or updated information. LSACK confirms successful receipt. Without these packets, OSPF routers would not be reliable to build or maintain an accurate view of the network. You will learn the details for each packet later in this chapter. For now, just remember that each packet has a specific role, and together they allow OSPF routers to discover neighbors, synchronize their database, and keep the network topology up to date. Now that we have seen how OSPF routers exchange information using different packet types, the next question is, where does all the information go? When an OSPF router receives routing information, it doesn't place it directly into the routing table. Instead, it stores the information in 3 different databases, or the data structures. Each database has a specific purpose. The first is the adjacency database, also known as the neighbor table. This table contains a list of all neighboring OSPF routers that have successfully formed an adjacency with the local router. You can think of it as routers contact list. Before routers can exchange routing information, they must first know who their neighbors are. The second is the link state database, the LSDB. The LSDB contains information about the entire network topology within the OSPF area. Instead of showing only the best routes, it stores all the link state information learned from every router. Because it represents the network map, we often call it topology table. The third is the forwarding table, the forwarding database. After OSPF runs the SPF algorithm and determines the best paths, those routes are placed in the forwarding table, the forwarding database. This information is then used to build the router's routing table, which is what the routers actually consults when forwarding packets. Each database serves a different purpose. In conclusion, the neighbor table tells us who are the neighbors. The topology table tells us what the networks look like. The routing table tells us which paths to use to reach each destination. All of these databases are stored in RAM, where RAM stands for Random Access Memory, so they can be updated quickly whenever the network changes. As routers exchange new information or detect topology change, the OSPF automatically updates this database to keep the routing information accurate. Later in the course, we'll learn the Cisco IOS commands used to display each of these tables so we can verify the OSPF is doing on a real router. Now let's see how OSPF actually decides which path is the best. After the router has collected information about the network and built its link state database or the topology table, it still needs to determine which route should be used to reach each destination. This is where the Dijkstra shortest path first, or SPF algorithm comes to play. Unlike RIP, which simply counts the number of hops, OSPF use costs as the routing metric. Every OSPF interface has a cost value, and as a packet travels through a network, those costs are added together. This total is called the accumulative cost. The SPF algorithm compares all possible paths and selects one with the lowest accumulative cost. Let's look at the figure. On the left is the link state database, which contains all the network topology information. In the middle, the router runs the SPF algorithm. You can think of this as the router analyzing all available paths through the network. During this process, the router assumes itself is the starting point, the root of the network. From that route, it calculates the shortest and the lowest cost path to every other router and the network. The result is shown on the right as the SPF tree. The SPF tree isn't the routing table itself. Instead, it's a decision tree that shows the best path from the local router to every destination in the OSPF area. Once the SPF tree has been created, OSPF extracts the best routes and places them into the forwarding table, the forwarding database. Finally, those routes are installed into routing table, which the router uses to forward packets. So the process is very straightforward. Build a link state database. Run the Dextra SPF algorithm. Create a SPF tree. Select the lowest cost routes. Install those routes into the routing table. Keep in mind that OSPF recalculates the SPF tree whenever the network topology changes. If a link fails or a new network is added, the router rerun the algorithm to ensure it's always using the most efficient path. 1.1.3 Link State Operation. Now that we understand the OSPF database and the SPF algorithm, let's put everything together and look at the complete OSPF routing process. The goal of OSPF is to reach a state called convergence. Convergence means that every router in the OSPF area has the same view of the network and agrees on the best path to every destination. In this example, we have a network of 5 routers. Notice that every link has a cost assigned to it. Remember, OSPF used cost, not hop count, to determine the best path. To reach convergence, every OSPF router follows the same 5 steps. 1. Establish neighbor adjacencies. 2. Exchange link state achievements. 3. Build a link state database. 4. Execute the SPF algorithm. 5. The best route. Now let's talk about step 1. Establish neighbor adjacencies. The first step is to discover neighboring routers. Each router sends hello packets out of its OSPF-enabled interface. When 2 routers receive each other's hello packets and their OSPF setting match, they establish a neighbor adjacency. Without neighbors, routers cannot exchange information, so it's always the first step. Step 2. Exchange link state achievements. After becoming neighbors, the routers begin exchanging link state achievements, or LSAs. Each router advertises information about its directly connected network and the cost of each link. These LSAs are flooded throughout the OSPF area so that every router eventually receives the same network information. Step 3. Build a link state database. Once all the LSAs have been received, each router builds its link state database, the LSDB. You can think of the LSDB as a complete map of the OSPF area. Since every router has received the same LSAs, every router should have an identical copy of the topology table, the database. Step 4. Execute the SPF algorithm. Next, the router runs the Dijkstra shortest path first, or the SPF algorithm. Using the information stored in the LSDB, the router calculates the lowest cost path from itself to every destination in the network. The result of this calculation is called the SPF tree. Step 5. Choose the best route. Finally, OSPF selects the best path from the SPF tree. These routes are installed into the routing table, and the router is now ready to forward packets using the most efficient path. At this point, the router has completed the routing process. Now let's talk about single area and multi-area OSPF. As a network grows larger, there are more routers, more links, and more routing information to process. If every router had to maintain information about an entire super large network, OSPF would become less efficient. To solve the problem, OSPF uses a hierarchical design based on areas. An OSPF area is simply a group of routers that share the same link state database, or LSDB. Because they all have the same topology information, routers within an area have an identical view of the area's network. There are two ways to deploy OSPF. The first is single area OSPF. The topology is shown here. The second one is multi-area OSPF, multiple smaller areas. For this course, we only focus on single area OSPF version 2. Once you understand how OSPF works within a single area, learning multi-area OSPF becomes much easier because it follows the same principle with additional hierarchy. In a single area design, every router belongs to the same OSPF area. The recommended practice is to use area 0, which is also known as the backbone area. Take a look at the figure here. Here, routers R1, R2, and R3 all belong to area 0. Since they are all in the same area, they share the same link state information and maintain identical topology database. Single area OSPF is the simplest design to configure and manage. It commonly used in small to medium-sized network because there is only one area to maintain. The second option is multi-area OSPF. 1.1.5 Multi-area OSPF. With multi-area OSPF, one large routing domain can be divided into smaller areas. To support hierarchical routing, routing still occurs between the areas, while many of the processor-intensive routing operations, such as recalculating the database, are kept within an area. For instance, anytime a router receives new information about a topology change within the area, the router must rerun the SPF algorithm, where SPF stands for the shortest path first, create a new SPF tree, and update the routing table. The SPF algorithm is CPU intensive, and the time it takes for the calculation depends on the size of the area. Routers in other areas receive updates regarding topology changes, but this router only updates the routing table, not run the SPF algorithm. Too many routers in one area would make the LSDBs very large and increase the load on the CPU. Therefore, arranging routers into area effectively partitions a potentially large database into smaller and more manageable database. The hierarchical topology design options with multi-area OSPF can offer the following advantages. The first one is smaller routing table. Tables are way smaller because there are fewer routing tables entries. This is because network addresses can be summarized between areas. Route summarization is not enabled by default. Also, that reduces the link state update overhead. Designing multi-area OSPF with smaller areas minimizes the processing and memory requirements. Reduce frequency of the SPF calculation. Multi-area OSPF localize the impact of topology change within an area. For instance, it minimizes routing update impact because LSA flooding stops at the area boundary. Instead of placing every router into one area, the network is divided into multiple smaller areas. This makes the OSPF much more scalable because routers only need detailed topology information for their own area. These multi-areas are connected together through Area 0, the backbone area. The routers that connect one area to other area called the area border routers, the ABRs. An ABR exchange routing information between different OSPF areas while keeping the detailed topology information separated. Using multiple areas reduce the amount of routing information each router must process, decrease the CPU and memory usage, and speed up the convergence in large networks. For example, in this figure, the router R2 is an ABR for Area 51. A topology change in the Area 51 will cause all area routers to return the SPF algorithm. Create a new SPF tree and update their IP routing tables. The ABR R2 would send an LSA to routers in the Area 0, which would eventually be flooded to all the routers in the OSPF routing domain. This type of LSA does not cause routers in other areas to rerun the SPF algorithm. They only have to update their LSDB and the routing table. 1.1.6 OSPF v3. OSPF v3 is the OSPF v2 equivalent for exchanging IPv6 prefixes. Recall that IPv6, the network address, is referred as the prefix and the subnet mask is called the prefix length. Similar to its IPv4 counterpart, OSPF v3 exchange routing information to populate the IPv6 routing table with remote prefixes. Let's use this picture to understand the OSPF v2 and the OSPF v3 can run on the same router. Look at R1 on the left. At the top, you can see OSPF v2, which is responsible for IPv4 network. Notice that OSPF v2 has its own neighbor table, topology table, and a routing table. Now let's look below it. The same router is also running OSPF v2 for the IPv6 network. OSPF v3 also has its own neighbor table, topology table, and the routing table. The same thing is true for R2. So even though both OSPF versions are running on the same physical router, they operate as two separate routing processes. OSPF v2 handles IPv4 only. OSPF v3 handles IPv6 only. They do not share their neighbor tables, topology databases, or routing tables. Think of it running two independent OSPF protocols on the same router. One manages IPv4 traffic and the other manages IPv6 traffic. The important point to remember is that the operation is almost identical. Both versions discover neighbors, exchange routing information, build topology tables, and calculate the best path using the SPF algorithm. The only major difference is which IP version they support. For OSPFv2, that support IPv4, and for OSPFv3, it supports IPv6. Everything else works in almost the same way.